Okay, so parametric equations. Okay, notice how it is plural. There's an S on the end there. What's happening? Just take a moment to look at this. Please don't write it down quite yet. All right. Basically, we have a set of two equations that are defined in terms of a third variable. So we have x equals something in terms of t, y equals something in terms of t, where t is what we call the parameter. That's why we call it parametric equations. Essentially, we're plugging values in for t to get x, y coordinates that create a graph. Okay, so go ahead and write down what you need to as far as that definition is concerned, and then I'll go through what they look like on a graph and an example so you can wrap your head around the idea of two equations to describe one picture. Now there's going to be a lot of different ways we can write parametric equations as far as describing a particular graph. But here's just an example so you can see kind of what it looks like. A rectangular equation, y equals negative x squared over 72 plus x. Okay, what would that give us? What kind of graph? A parabola, how do you know that? There's an x squared, okay? Here is a set of parametric equations that would be describing this parabola, okay? So we have an equation for x that has a t in it. We have an equation for y in terms of t. And what happens is we plug values into t to get x, y coordinates. Now what's going to happen, T doesn't always stand for time. However, if we're working on an application problem, what is T going to stand for? Time, okay? So that's kind of where we will be heading with that tomorrow. But for right now, let's just think about, on a number line, we're going to plug values in ascending order, right? If we start with -5, then we plug in a -4, then we plug in -3, and we keep getting bigger with our t values. So since we plug in values for t, what's happening is we have some direction to our graph. So this is the graph that matches the parametric equation set. It has direction to it, and this is what's going to set apart your rectangular graphs from your parametric graphs, is that we have to include the direction of the curve by putting arrows on it. Now, it's pretty quiet in here today. I'm going to make you talk to each other for a little bit. I want you to just brainstorm at your pod. How do you know what direction the arrows are going to go? How might we be able to figure that out? Go ahead and have a 60-second conversation. want to listen to it.
I was thinking like if the team, if you play in positive values for T.
Okay, Caleb just asked if we plug in positive values, wouldn't we be going to the right with the arrows? I know. So we could have something like this. That's a graph we'll look at later. Okay. Who has an idea? Why are the arrows going the way that they're going? Or how will we be able to figure out which direction the arrows go? How to with yes or no? Okay, so let's maybe plug in a couple numbers, okay, since that's kind of what a couple of you guys talked about. What happens if we plug in 1 to these, right? We get 24 radical 2, and then we get -16 plus 24 radical 2. Okay. Let me get my calculator real quick. So that point would be right here. Okay? This would be the point at t equals 1. Okay? If we plug in t equals 2, over right here. Okay? Also, I'll point out that right here is t equals 0. Okay? So do you see how here we have t equals 0, here we have t equals 1, here we have t equals 2. So it's not necessarily that t is positive, but what's happening as we get bigger with our t's, right? As we ascend with our t values, our curve is going to have to follow those coordinates, okay? So from t is 0 to t is 1 to t is 2, that's how we know the direction of our curve. Okay? All right. Go ahead and write down this. Write down x is t squared minus 4, and y is t over 2. You're not always going to get this, but I'm giving it to you right now. I'm giving that I want you to only graph between -2 and 3 for t. There are going to be 2 different ways I'm going to show you how to graph. We're going to start basic with this way, okay? First of all, it's helpful that I'm giving you where t is going to be restricted. So t is between -2 and 3. And then we have an equation for x and an equation for y. All right? What do you think we need to do? Okay? Okay, 0, 1, and 2 would be good to plug in. Should that be the only point to plug in? Probably not, okay? We'll want to figure out where it begins and where it ends and what's happening in between. So if you remember back in like Algebra 1 when you made XY charts, we haven't really done those for a while, right? One option for graphing would be to make a T, X, Y chart. When we plug in a value for t, what do we get for its coordinate? So our domain, essentially, because we're talking about a function in terms of t. T is telling us what our domain would be. Our domain is from -2 to 3. So we are going to plug in points from -2 to 3. All right, so what's that going to look like? If we plug in -2 into our x equation, what is our x value? 0. And in our y equation, -1. Okay. -1, if we plug that into our x equation, -1 squared minus 4 would give us -3. And if we plug that into our y equation, t over 2 would be -1/2. When we plug in 0, 0 squared minus 4 would be -4. 0 over 2 would be 0. Take about a minute and find me these next 3 points by plugging those t values into the x and to the y equation. Well, I was going to try to get a different one. Okay, what's the coordinate for t equals 1? -3, 1/2. T equals 2. 0, 1. And then t equals 3. 5, 3/2. Courtney read those off for me. Do you agree? Okay. So now watch and pay attention to the order we plot these points. Okay, we began with t equals 2. 0, -1. Then we moved on to t equals -1. -3, -1/2. T equals 0 is -4, 0. T is 1, -3, +1/2. T is 2 is 0, 1. And then t is 3 is 5, 3/2. Okay? So if we follow the order of our t values, we plotted these points in this order. So we would need to indicate those arrows in that manner. Yes?
Are you only supposed to drop 2 arrows? Or can
You can do more arrows. As long as I get an idea. First of all, Caleb, draw more than one. But just put enough arrows to where I can get an idea of the direction. Like if you feel like you want another one right there, go for it. Okay? But at least 2. Okay? Would be good. Okay? Okay? All right. Now, as far as these graphs go, without the arrows, it's not a parametric curve. So if you don't have the arrows on your graph, you will miss points. I need to be straightforward with you there. Okay? Make sure you indicate the orientation. Okay? Let's do another one. Okay? X equals the square root of t. and y equals t plus 2. Okay. Here is a time where I don't tell you where to begin, do I? However, do we know something about either the x and or y equation that can help us know where to begin? Caleb, I know you have an idea, but I want you guys to talk about ideas first, and then I'll come back to you, okay? Do we know where to start even though they didn't give it to us straight? Okay. Caleb, you were very excited about this, so I will let you answer. How do we know where to start?
I would say 0.
T equals 0, and why?
Because like the x is radical t, so it's like one of those graphs where it starts at 0 and goes to the right only.
Okay. We know that the domain of our x equation would be t is greater than or equal to 0 because we can't have negatives under the radical. Now, technically, our y equation is linear and it could be all real numbers, but we have to look at where those overlap. I can't plug negative values into the x equation, so we can't plug negative values into the y equation. So what we're going to have to do is we are going to have to start at t is 0. Okay? And I would just get a couple points until you have an idea of what this looks like. Okay? So we'll start with 0. When we plug in 0, we get 0 and then 2. When we plug in 1, square root of 1 is 1. 1 plus 2 is 3. Okay. Now, we can be a little bit strategic about this. If we plug in 2, we would get the coordinate square root of 2, 4. How many of you want to graph that coordinate and feel confident about your accuracy? I mean, we could graph it, but we're not going to be super accurate. Okay? My suggestion to you, if you don't have to, don't plug in a point that's going to be messy. Okay? 2 is going to be messy. 3 is going to be messy. 4, will that give us a nice number? Okay. 4 would give us a nice number. 4 would give us the coordinate 2, 6. Okay. And I think we have enough to kind of know our shape. What does that look like? Looks like half of a parabola, doesn't it? Okay. And it doesn't have an end to it. It's going to keep going. All right. There wasn't like an interval that's saying, hey, we stop here. So it's going to keep going, but we're also going to have that direction for the parametric curve. Now, is this how we want to graph every single time? It is? You just want to plug in points and figure out what shape it is? What if it's like a crazy, like, cubic function or a sine curve, or you're just going to deal with it? Figure out what graph it is all the time? Okay. So far I've given you some pretty nice graphs, okay? Not all the time will we get nice graphs, all right? So we are going to do what's called eliminating the parameter, okay? When we get a set of parametric equations, it is possible for us to take that set of parametric equations and squish them together to make just one rectangular equation, okay? So it's kind of like when we had polar equations and we converted them to to rectangular. We're doing the same thing, however, Eli, it's not as bad. It's not as bad. Okay? So, the purpose, like I said, of eliminating the parameter is so we can take a set of parametric equations and squish it down to just one rectangular equation. And while I pull up my calculator to show you something in the calculator, I want you to talk about at your table any ideas you have for taking these two equations and making them one. So essentially, we're getting rid of t, and I only want one equation with x and y. Okay? You have 1 minute to talk about it. All right, who has an idea? What's your idea? Solve for t in one equation, plug it into the other one. Sounds perfect. Okay? How many of you had that same discussion? Good. Okay, if we're trying to get rid of t, solve for t so you can substitute it into the other equation to be in terms of x and y. Okay? I do have a simplify step. Okay? If it's in an equation that we can write to be more recognizable, I would ask you to do that. Okay? Like if it's a parabola, we know how those should look. If it's a circle, I want you to write it in the circle form. Okay? If it's a line, write it in a nice form. Okay? So we're going to go back to our very first example. Yes. So the purpose of eliminating the parameter would be to get rid of the t, and we now have a rectangular equation. So what we could do is we can take our rectangular equation and graph it with our knowledge of what graphs look like, and then go back and think about the t values as we plug in and indicate the orientation that way. Does that make sense? Okay. Okay, so we're going to go back to this equation right here, or this set of parametric equations, and we're going to eliminate this parameter. Okay, so I want you to think about x and y. We need to solve for t. How many of you would choose the x equation to solve for t? How many of you would choose the y equation to solve for t? Okay, Callie, why are you picking y over x? Yeah, you don't want to deal with radicals in the x one. And we would have like plus or minus, and ew, who wants to deal with that? The y equation is simpler because it's linear versus quadratic. Let's solve for t there. So we know that y equals 2t. I totally said that backwards. I apologize. t equals 2y. That looks a lot better. Okay. It's a Monday, right? So then what we can do is we can take that and we can plug it in for this t here. So x equals t squared minus 4. Okay, so now, all right, we have a parabola, right? Okay, we just got done with the conics chapter, didn't we? Yeah. So we know that we could factor this guy out here. And in standard form, we would have 1/4 x equals y squared minus 1. Oh, hold on. Just kidding. I'm getting too excited, aren't I? We would need to complete the square first, wouldn't we? Just kidding. So the numbers just look so nice. Okay. What we can do is we can add this over. X plus 4 equals 4y squared. And then we could say y squared is 1/4 x plus 4. Where we have a vertex at -4, 0. Hey, I think that's where we had it last time. Yes. Well, we're dividing the quantity by 4, which is why I have the 1/4 out here. Okay, but we need to have that x with a coefficient of 1 so we can identify the vertex. Okay, so we have a parabola with vertex -4, 0. It's opening to the left, and it's really super skinny because we have that 1/4 as our coefficient. Okay, which matches this graph that we have right here, right? Okay, those two would be the same. Okay. I want to come back to this one because this one would be like here I gave you the interval, right? That it was easier to just plug in numbers. Okay, here this would be a time where maybe eliminating the parameter would be an easier way of graphing it. Okay, so let's go back to this one and I want to eliminate the parameter here. Okay. Now, here we could eliminate the parameter using either the x or the y. Okay. But which one's going to give us like a quadratic equation? Can you see it? Okay, if we choose the x, it's going to give us a nice quadratic equation, and let's see what that looks like. If we take x equals radical t, and we solve for t, that means t equals x squared. Okay. Well, if y equals t plus 2, then hey, y equals x squared plus 2. Boom, we're done. Okay. Now, if you're eliminating the parameter, we also have to think about the domain. Because if we eliminate the parameter, how many of you are going to be tempted to draw a full parabola here? Like, sweet, x squared plus 2, I'm going to draw a parabola, shift it up 2. Okay, but why do we need to be careful? Originally, we had the square root of t, and we said t has to be greater than or equal to 0. I cannot plug in any negative numbers. Well, if t is going to be greater than or equal to 0, that's going to affect our domain. Okay? Well, when we plug in 0, we're at the coordinate 0, 2. All right? Take note of that x is 0. So what we're going to have to do is we're going to have to come down here, and we're going to have to specify that x is greater than or equal to 0. Okay, we have to specify our domain based on what we had in our parametric equations. Don't be tricked by the domain. Okay, if you have a square root in your parametric equation, that really needs to stick out to you, and you need to be careful with the domain. Okay, what else would we need to be careful about with as far as domain is concerned? Square roots give us some issues. What else? We can't plug negative numbers into a radical. Something in the denominator. We can't divide by 0. So that's something else we would need to be watching for.
Would we ever have one where we have to graph one with like asymptotes or like a whole?
I'm glad you brought that up. You think that I'm going to change my example based on his question? This is the example we were going to do anyway. Let's look at this one. Okay. Actually, though, before I do that, can I take a timeout? I want to go back to this one and show you what this looks like in a graphing calculator. Did you know that you have a parametric mode in your calculator? Oh. If you go to mode, you have a PAR, parametric mode, which means when you go into Y equals, you have an X equals and a T equals. Isn't that cool? So we can put the square root of T in here. When you press this button right here, it's going to give you T instead of an X. And then for Y, T plus 2. But I want everybody to watch my calculator. Are you watching? You see how it draws it? What do you think that corresponds with? The direction, yeah. Your calculator is going to draw it in that order. Okay? Now, I will say that if you go to window, it does have T beginning at 0 and T stopping at 6. So if you don't get the full picture, you're going to have to make T max a larger number. Okay.
Wait, we get our calculator from this one. What's the test?
Yeah. Back to this one. Yes.
Does it matter if our calculators are radians or degrees?
If you have any sort of trig function, it has to be in radians. Otherwise, it would not matter. Okay. Okay, so write this down if you didn't get to before I took a time out. Okay, and then take 10 seconds to, at your table, decide which variable, x or y, do we want to solve for t to eliminate the parameter. You would do 6.
How would you do y? That's just too much work.
I feel like we could just plug x in for 2 minus y equals 2.
All right, Maverick, what do you think, x or y? I think x is an excellent choice. All you have to do is add 1 over, and boom, you've solved for t. I don't know if it's even possible. Well, I mean, it would be very, very messy to solve for t in the y equation. You could do it, but it's going to be messy. Okay. All right, so now we can plug in x plus 1 in for each of our t's. Okay. Now I got excited here. Do we have any domain issues with our parametric equations? Hey, Grace, what issue do we have? Okay, here we know that t cannot equal 1. Okay, we'll come back to that. Now here, when we reduce our equation, we have x plus 1 all over x. Okay? Now let's think about this domain. This domain we would have to be careful because we can't have x equaling 0. What I want you to notice about that, when we plug in 1 for t, what would we get for x? 0, okay? So in our parametric equations, t cannot be 1, which would correspond to our rectangular equation, x cannot be 0. Okay? All right, so anyone remember what these graphs look like? No? Well, x equals 0 means what? Like x cannot equal 0. What's happening there? We have a
Hole. Asymptote.
Yeah, an asymptote. Good job. At x equals 0, we have an asymptote. We have holes and we have factors that cancel. That's not going to happen here. Okay? Now, both of these are of the same degree, which means our horizontal asymptote is at 1.
So remember that.
Okay? Since we have the same degree, we look at the coefficient for the horizontal asymptote. Okay? So, okay, I'm not going to be too picky about what's happening. We just know we have these branches here. Okay? However, we need orientation, right? We need those arrows. No? Look at this. What happens if we plug in 1? If we plug in 1, oh, we can't plug in 1. If we plug in 2, Eli, if we plug in 2, we are at 1, 2. If we plug in 3, we are at 2. Okay. So we went from here to here. Okay. And then we can do the same thing over here with negative t values. Take a moment to figure out the orientation of this bottom one.
I mean, I don't know why I would stress myself out plugging it in. Get the calculator.
I guess wrong.
If we plug in like -5 and then plug in -4 and then plug in -3, those are going to get closer and closer to our -1, which is where we have the asymptote. Okay. All right, last one. This is my favorite. You ready? The t doesn't always have to be the parameter. Sometimes theta is our parameter. Well, you would want to make sure you plug in like -3 first and then -2 because -2 is bigger. So you want to go from smaller to bigger numbers. So if you plug in -3, then plug in -2, you would want to follow that arrow. Does that make sense? I think you plugged them in the reverse order.
Seems like
Yeah.
I don't understand why we do that in this.
Okay, so how are we going to get rid of theta?
The bottom right there.
Okay, so you're thinking of polar. Okay, and if this was polar, then yes, I would say we could go for that. But this is parametric. Okay. And do you see how the 3 and the 4 are different numbers? Okay. Why can we not divide by theta?
You just can't.
Because you do, okay, it's inside the trig function, okay? And yeah, we could divide, we could divide the 3 over to get cosine theta, but then what are we going to do with that? Inverse cosine of x over 3 equals theta? Is that something we want to plug into the other one?
I think this is one where you just make that chart.
What chart?
Instead of
The
eliminating.
TXY.
I'm going to flash back to identities. Is this true? Callie. We just saw that the cosine of theta is x over 3, right? So the cosine of theta is x over 3. Right? The sine of theta is y over 4. What do we have, guys?
Circle.
Ish.
Oh.
We have an ellipse. And what do we know about our ellipse? We know that the center is at 0, 0. We know vertically A is 4. B is 3. Okay. Now we have to figure out which direction this guy's going. No, 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 no. Okay, this really isn't that bad.
Just do 0.
I wouldn't even do 1. I would plug in 0 and then I would plug in pi over 2. So if we plug in 0, we have x equals 3 times the cosine of 0. Y equals 4 times the sine of 0. That gives us this coordinate right here. If we then plug in pi over 2, x equals 3 times the cosine of pi over 2. Y equals 4 times the sine of pi over 2. We're at this coordinate right here. They're going counterclockwise. Okay. I just plug those in because those are nice values to plug in. You can plug in pi over 4 if you want to. It's just not going to be a pretty number. Okay. All right. Your last book assignment, seniors, is tonight. Juniors, you still have a couple book assignments, but we'll leave those till after the final. Okay? So seniors, your last book assignment is tonight. Please make sure that when you graph, you indicate the orientation. Tomorrow, we're going to talk about projectile motion. You'll get a worksheet, and your test is Thursday. All right?
Say